In the immense, starless expanse of the cosmos, a realm exists where the very fabric of space-time unravels. Here, the familiar laws of physics dissolve, and reality itself contorts beyond comprehension. We name this terrifying phenomenon a black hole. But consider this: what if everything we perceive, everything within our observable universe, is actually confined within one of these cosmic traps? Recent findings from the James Webb Space Telescope have profoundly impacted the field of astronomy, unveiling patterns incompatible with a truly random universe. Prepare for a journey that will challenge your fundamental understanding of reality. Let us commence. Envision plunging through a doorway that instantly seals shut behind you. This is the stark reality of a black hole's event horizon, a spatial boundary beyond which escape becomes utterly impossible. Even light, the fastest entity in the universe, becomes ensnared in an inescapable descent towards annihilation. This event horizon marks the point of no return, a spherical boundary of destruction encircling the most extreme objects in our universe. But here's the truly astonishing aspect. The dimensions of this cosmic prison are directly proportional to the amount of matter it consumes. Double the mass, and you double the diameter. 10 times the mass results in a black hole 10 times larger. This isn't merely a theoretical equation. It's a linear relationship consistently observed throughout the cosmos, from stellar mass black holes to the supermassive behemoths residing at galactic centers. Now for the truly staggering calculation. When astrophysicists utilize the total mass of our observable universe and pose a straightforward question, what size would a black hole containing this mass be? The response is breathtaking. The event horizon would extend approximately 93 billion light-years, remarkably consistent with the size of our cosmic horizon, the maximum distance from which light has had sufficient time to reach us since the universe's inception. This is not merely a fortuitous coincidence. The average density of matter within our cosmic horizon precisely matches that expected inside a black hole of comparable, immense size. It is as if our entire universe were compressed to the exact density needed for gravitational collapse. Yet we comfortably inhabit this cosmic prison, unaware. The mathematics become more fascinating when considering Einstein's general relativity's predictions regarding a black hole's interior. Instead of annihilation, the equations suggest a completely new space-time emerges beyond the collapse. Surviving a journey through a black hole would reveal the entire future history of the departed universe, unfolding in accelerated time. Simultaneously, an entirely new cosmos would commence its expansion and evolution. This presents modern cosmology's most profound question. Could we reside within this newly formed universe? Are we the consequence of some ancient cosmic collapse in an unobservable, unreachable universe? Our universe exhibits remarkable signs of specific initial conditions, precise fundamental constant values, a particular geometry, and evidence suggesting inherited angular momentum from a parent universe. The implications transcend academic curiosity. If our universe truly exists within a black hole, then every black hole in our cosmos might harbor its own nascent universe, isolated by the event horizon's one-way nature. Entire civilizations, countless worlds, infinite possibilities could exist beyond these dark boundaries, forever hidden from our observation, yet real and thriving in their own pocket dimensions of reality. The discovery of our cosmic prison story begins with Roger Penrose, a brilliant physicist, and his mathematical proof seemingly sealing our fate. In 1965, Penrose demonstrated that, under very general conditions, gravitational collapse inevitably leads to a singularity, a point where matter crushes itself to infinite density, rendering the laws of physics inapplicable. This singularity theorem became foundational to our understanding of black holes, later extended by Stephen Hawking and others, demonstrating these mathematical entities' inevitability in our universe. For decades, scientists accepted that anything falling into a black hole would be incomprehensibly compressed, crushed to zero volume, where time ceases and space loses all meaning. However, Penrose's theorem relied on classical physics, the familiar realm of everyday objects and predictable forces. Quantum mechanics alters everything. At the subatomic level, particles defy classical rules, exhibiting behaviors seemingly impossible in our daily lives. The quantum world operates on fundamentally different principles, including the exclusion principle. This principle dictates that no two identical particles can occupy the same quantum state. Consider it nature's ultimate traffic regulation. Particles with identical properties cannot occupy the same space, regardless of pressure. As matter collapses toward a black hole's center, this quantum traffic jam becomes critical. Recent calculations by researchers at the University of Portsmouth reveal something extraordinary. When quantum effects are correctly incorporated into the mathematics of gravitational collapse, the inevitable singularity vanishes. Instead of crushing matter into nothingness, the collapse reaches maximum density, then rebounds like a cosmic rubber ball, striking an invisible wall, rebounding with tremendous force. This bounce requires no exotic physics or mysterious new particles. It naturally arises from combining Einstein's general relativity with basic quantum mechanics, two theories we already understand and trust. The mathematics show that as collapsing matter approaches the potential singularity, quantum pressure builds until it overcomes gravity, reversing the collapse. The outcome of this cosmic rebound is remarkable, a new expanding universe with properties closely matching our observable cosmos. The bounce naturally produces two phases of accelerated expansion, mirroring both early universe cosmic inflation and the mysterious dark energy driving current acceleration. No hypothetical fields or speculative physics are required, only the inevitable consequence of quantum mechanics preventing infinite compression. Therefore, our Big Bang might not be the beginning of everything, but rather the moment of maximum compression followed by explosive expansion in a potentially endless cosmic cycle. We exist not at time's start, but potentially within an eternal dance between collapse and expansion, between ending and beginning. The universe born from a prior cosmos imprinted its origins ubiquitously, in the precise values of fundamental physical constants, the very geometry of space, and potentially the rotational orientation of galaxies across the observable universe. At Kansas State University, computer scientist Lior Shamir unearthed a discovery poised to revolutionize cosmology. Utilizing imagery from the James Webb Space Telescope's Advanced Deep Extragalactic Survey, he scrutinized a seemingly random phenomenon, the rotational direction of spiral galaxies as observed from Earth. In a truly random universe, one would anticipate an approximately equal distribution of clockwise and counterclockwise galactic rotations, analogous to a cosmic coin toss. Minor deviations would be mere statistical noise, insignificant fluctuations averaging out over extensive datasets. However, Shamir's analysis of 263 deep universe galaxies revealed an anomaly. 60% rotated clockwise, only 40% rotated counterclockwise. The probability of this occurrence by chance was less than 0.07%, astronomically improbable in a universe governed by randomness. A mechanism was imposing a preferential rotational direction on the grandest scales, contradicting fundamental assumptions about cosmic symmetry. This finding wasn't entirely unforeseen. Prior observations using ground-based telescopes had hinted at similar asymmetries, but the James Webb Space Telescope's unparalleled deep universe observational capabilities unveiled the pattern with striking clarity. Even more intriguing, the asymmetry intensified when examining more distant galaxies, objects viewed as they existed billions of years ago, during the universe's infancy. The pattern exhibited another peculiar characteristic. The asymmetry peaked near the galactic poles, the directions perpendicular to our Milky Way's plane. This suggested a connection between the preferential rotation and our galaxy's spatial orientation, as if a cosmic axis existed, influencing galactic formation and evolution. Shamir employed an automated computer program, Ganalyzer, to categorize each galaxy's rotation, eliminating human bias. The program transforms galaxy images into radial intensity plots, detecting spiral arm curvature to determine rotational direction. This objective, replicable methodology revealed the cosmic asymmetry with mathematically precise, verifiable results. The implications were profound. If galaxies truly favored one rotational direction, the universe would be anisotropic, not uniform in all directions. This would violate the cosmological principle, a cornerstone of our understanding of cosmic evolution. The universe would possess an inherent asymmetry, a preferential axis or direction influencing galaxy formation and rotation across billions of light years. But what could generate such a large-scale preference? In our everyday experience, objects rotate due to an initiating force, as seen in diverse phenomena from ice skaters to gravitationally collapsing gas clouds. Conservation of angular momentum amplifies initial rotation as objects contract. However, this doesn't explain a preferred spin direction for the universe itself. The answer might reside in the most extreme objects known to physics, rapidly rotating black holes, capable of influencing spacetime across vast distances. Every black hole rotates, an observational fact etched into spacetime. When massive stars collapse, they inherit and amplify their progenitor star's rotation to extraordinary levels. Conservation of angular momentum transforms a slowly rotating stellar giant into a cosmic spacetime vortex, spinning so rapidly it drags space and time along. Here the narrative takes a truly astonishing turn. According to black hole physics, only two pieces of information, total mass and angular momentum, can traverse the event horizon from the external universe. All else, chemical composition, temperature, magnetic fields, even the complex formation history, is erased. The black hole becomes a simple object defined solely by its mass and spin rate. If our universe resides within a black hole, it must have inherited the angular momentum of its progenitor. This inherited spin would manifest as a cosmic axis, a preferential direction woven into spacetime's fabric, influencing matter movement and galactic formation across our observable cosmos. Consider it cosmic DNA. As organisms inherit traits, our universe would carry its parent black hole's rotational signature. This inheritance wouldn't be apparent in everyday phenomena. The effect would be too subtle for local physics detection. But across cosmic distances and billions of years, this inherited spin could accumulate into the galaxy rotation asymmetry detected by the James Webb. Theoretical physicist Nikodem Popławski of the University of New Haven has championed this theory for years. In his model, matter falling into a black hole doesn't collapse into a singularity. Instead, quantum effects prevent infinite compression, causing the matter to rebound and expand into a new universe beyond the event horizon. This new cosmos appears isolated from its parent, connected only through spacetime's warped geometry. The parent universe would appear as a white hole, the theoretical opposite of a black hole, inaccessible from the outside and emitting matter and energy. However, we couldn't observe this white hole, as it would lie beyond our cosmic horizon, in space-time regions unreachable by light from our universe. This presents a breathtaking picture of cosmic evolution. Every black hole in our universe could be a new cosmos's birthplace, generating baby universes inheriting their parents' angular momentum and fundamental properties. These universes would be entirely isolated from us, developing their own galaxies, stars, planets, and potentially life, forever hidden behind the event horizon's one-way barrier. The asymmetry in galaxy rotation becomes a fossil record of our cosmic birth, preserved across 13.8 billion years of universal evolution. It's our parent black hole's signature, inscribed in the spin of galaxies across the observable universe, awaiting billions of years for beings like us to develop the telescopes powerful enough to decipher this ancient cosmic message. In 2022, the James Webb Space Telescope, a $10 billion marvel of astronomical engineering, opened its golden eyes upon the universe. This was not merely an incremental advancement, it represented a complete revolution in our capacity to observe cosmic history. This instrument possesses the ability to peer deeper into space, and therefore farther back in time, than any device humankind has ever constructed, unveiling the universe as it existed in its youth. A time of wild, dramatic differences from the present day. The telescope's unparalleled infrared vision allows it to penetrate cosmic dust and detect the light emanating from the very first galaxies formed following the Big Bang. However, the true power of the James Webb lies in its capacity to capture minute details across immense cosmic distances, revealing with unprecedented clarity the complex structure and movement of galaxies that existed billions of years ago, a level of detail unimaginable only decades prior. This revolutionary capability enabled Lior Shamir's discovery of galaxy rotation asymmetry. While earlier ground-based surveys had hinted at similar patterns, they lacked the resolution and depth necessary for conclusive measurements. The James Webb Space Telescope transformed this field, providing crystal-clear images of hundreds of distant galaxies, each a snapshot of cosmic conditions from the universe's earliest epochs. The Advanced Deep Extragalactic Survey, or JADIS, constitutes one of the most extensive and comprehensive deep-field imaging programs ever undertaken, focusing on thoroughly studied regions such as the Great Observatory's Origins deep survey fields. JADIS builds upon decades of prior observations while simultaneously pushing the boundaries of detectability and measurement in the distant universe. The exceptional power of these observations stems from their objectivity. Shamir's team employed automated computer algorithms to analyze galaxy shapes and ascertain rotation directions, thus eliminating the potential for human bias to skew the results. The Ganalyzer program converts each galaxy image into mathematical data, identifying spiral arm patterns and classifying rotation with reproducible precision verifiable by any researcher. The findings were irrefutable. Galaxy after galaxy exhibited the same preference for clockwise rotation when viewed from Earth. This pattern was neither subtle nor marginal. It was a clear, statistically significant departure from randomness demanding explanation. Even more strikingly, the asymmetry appeared stronger in more distant galaxies, implying that the underlying cause of this cosmic preference was more pronounced in the early universe. The James Webb's observations also revealed another vital detail. The rotation asymmetry peaked near the galactic poles, with distinct patterns at the northern and southern poles relative to our Milky Way. This suggested that the effect was not simply random cosmic structure, but possessed a specific geometric relationship to our position and orientation within the universe. These discoveries mark only the beginning of the James Webb's contributions to cosmology. The telescope continues to observe the deep universe, amassing larger samples of distant galaxies and potentially confirming whether the rotation asymmetry represents a fundamental characteristic of cosmic structure or stems from more commonplace observational effects. If corroborated by further observations, the James Webb Galaxy rotation discovery could compel astronomers to completely reconsider their understanding of cosmic evolution, the nature of space-time, and our place within what may be the most intricate cosmic prison ever conceived, a universe perpetually trapped within the event horizon of an unimaginably massive black hole. The mathematics describing our potential cosmic confinement are both elegant and terrifying in their implications. When Einstein formulated his field equations for general relativity, he created a mathematical framework capable of describing the most extreme objects in the universe, including black holes so massive they could encompass entire cosmoses within their event horizons. The key insight arises from comprehending how black holes scale with mass. Unlike everyday objects, where doubling the mass might double the weight but only slightly increase the size, black holes exhibit a linear relationship between mass and radius. This means a black hole with twice the mass possesses exactly twice the diameter. 10 times the mass results in an event horizon 10 times larger. This scaling continues indefinitely, with no theoretical upper limit on the size a black hole can attain. When cosmologists perform the calculation for our entire observable universe, incorporating every galaxy, star, planet, and particle within our cosmic horizon, and determine the size of a black hole needed to contain this mass, the answer is shockingly precise. The resulting event horizon would measure approximately 93 billion light-years across, almost precisely matching the size of our observable universe. But the correspondence extends beyond mere size. The average density of matter within our cosmic horizon equals approximately 10 to the negative 27th power kilograms per meter cubed. This incredibly low density, far less than the best vacuum achievable in laboratories, precisely matches what general relativity predicts for the interior of a black hole with our universe's mass and size. This density match is not approximate or close. It is exact within our current measurement uncertainties. It is as if our universe were perfectly designed to fit within the event horizon of a cosmic black hole, with every parameter finely tuned to facilitate this extraordinary coincidence. We are either witnessing the most remarkable accident in cosmic history, or our universe truly resides within such a gravitational prison. The mathematics become even more compelling when rotation is included. If our universe inherited angular momentum from a parent black hole, this would create what physicists term a Kerr black hole, a rotating solution to Einstein's equations that drags space-time along with it. This rotation would establish a cosmic axis, a preferred direction that could influence how matter moves and galaxies form across billions of years of cosmic evolution. Recent calculations by researchers at the University of Portsmouth indicate that quantum mechanics prevents the infinite compression that classical physics predicts at black hole centers. Instead of forming a singularity, collapsing matter attains maximum density and then rebounds, expanding into a new universe with properties remarkably similar to our observed cosmos. This quantum bounce generates two distinct phases of accelerated expansion, one corresponding to cosmic inflation in the early universe and another matching the dark energy currently driving universal expansion. Both emerge naturally from the mathematics without requiring hypothetical particles or enigmatic energy fields. The equations suggest that our Big Bang was not the beginning of time, but rather the moment when quantum pressure overcame gravitational collapse, transforming destruction into creation and giving birth to our expanding cosmos within the protective confines of a cosmic event horizon that we can neither see nor escape. We exist within multiple horizons, each a boundary beyond which certain types of information can never reach us. The most familiar is our cosmic horizon. The distance light has traveled since the Big Bang, creating a sphere around Earth beyond which we can observe nothing. But if we exist inside a black hole, we confront an even more fundamental boundary, the event horizon separating our universe from the parent cosmos that created us. This presents a profound paradox in our understanding of cosmic evolution. Traditional cosmology assumes our universe is open and infinite, expanding into empty space without barriers to constrain its growth. But if we reside within a black hole, our entire cosmos is enclosed within a finite boundary that we can never observe or traverse. We are, in essence, prisoners within the ultimate cosmic prison, utterly unaware of our confinement. The event horizon encompassing us operates under physics' most peculiar laws. Information can traverse this boundary inward, but never outward. This implies our universe could receive matter and energy from a parent cosmos. However, nothing we create or discover can ever escape to influence the larger reality beyond our cosmic confines. From the perspective of observers in the parent universe, our entire cosmic history would unfold in an instant. Time dilation near the event horizon would compress our 13.8 billion years of evolution into mere moments, as viewed from outside. Stars would be born, complete their life cycles, and die in what would seem to external observers as a fleeting flash of light before vanishing forever behind the horizon. Yet, from our internal viewpoint, time flows normally. We experience the full richness of cosmic evolution, galaxies forming, stars igniting, planets nurturing life, and civilizations arising to ponder their place in the universe. The horizon imprisoning us remains perpetually invisible, forever beyond our capacity for direct detection or measurement. This imprisonment is not merely theoretical. If our universe resides within a black hole, then every black hole we observe in our cosmos could contain its own universe, replete with galaxies, stars, and potentially intelligent life. These nested universes would be completely isolated from us and each other, generating an infinite hierarchy of cosmic realities. The James Webb Space Telescope's discovery of galaxy rotation asymmetry might provide our first direct evidence of this cosmic imprisonment. The preferential rotation direction could be the signature of our parent black hole, inscribed into the fabric of space-time itself and preserved across billions of years of cosmic evolution. It is akin to discovering a cosmic fingerprint revealing our true origin. This, however, raises unsettling questions concerning the nature of reality. If we can never escape our cosmic prison, if we can never communicate with or observe the parent universe that birthed us, does our existence within a black hole even matter? Our physics, our chemistry, our biology, all function precisely as observed. The stars still shine. Planets still orbit. Life still evolves. Perhaps the most profound implication is that our universe might be only one among countless cosmic bubbles. Each harbors its own version of physics, its own galaxies, its own potential for life and intelligence, all sealed off from one another by the fundamental laws governing black holes and the flow of information across event horizons. At the core of black hole cosmology lies one of theoretical physics' most mind-bending concepts, the white hole. If black holes are cosmic vacuum cleaners, drawing everything inward past a point of no return, then white holes are their precise opposites, cosmic fountains spewing matter and energy outward with such force that nothing can ever enter them from the outside. Einstein's equations possess mathematical symmetry. For every black hole solution describing inward matter flow, there exists a corresponding white hole solution where everything flows outward. While we have never observed a white hole in our universe, they represent a crucial piece of the cosmic puzzle if our reality truly exists within a black hole. According to the black hole universe theory, the Big Bang was not an explosion from nothingness. It was our first glimpse of a white hole. The white hole represents the other side of the parent black hole that gave birth to our cosmos. All the matter and energy that fell into the parent black hole eventually emerged through this white hole connection, expanding to create the galaxies, stars, and planets we observe today. This paints a breathtaking picture of cosmic recycling. Matter from the parent universe collapsed through a black hole, traversed a region of warped space-time where the normal rules of physics break down, and then exploded outward through a white hole to initiate our universal expansion. The white hole becomes the source of our cosmic horizon, the point from which all matter and energy in our universe ultimately originated. But here lies the crucial detail. We can never directly observe this white hole. It exists beyond our cosmic horizon, in a region of space-time that light from our universe can never reach. The white hole manifests to us as the distant past, the moment of cosmic origin that we can approach but never quite attain through observation. The white hole connection explains several enigmatic features of our universe. It accounts for why the cosmic microwave background, the afterglow of the Big Bang, appears so uniform across the sky. This radiation represents the last light from the white hole region, stretched and cooled by billions of years of cosmic expansion, yet still bearing the signature of our cosmic birth. It also explains the arrow of time, why time flows forward rather than backward in our universe. The white hole establishes a preferred direction for the flow of causality, inherited from the parent black hole's internal geometry. Time flows from the white hole region toward our present cosmic era, creating the temporal asymmetry that allows for the evolution of complexity, life, and consciousness. Recent mathematical research suggests that white holes may not be purely theoretical constructs. Quantum phenomena at a black hole's core could generate the conditions needed for white hole formation, transforming what seems like cosmic destruction into cosmic creation. The rebound effect preventing gravitational singularities could manifest as a white hole explosion, propelling new universes from the hearts of expiring black holes. This implies our cosmic origin narrative is actually a cycle of death and rebirth, where the gravitational collapse forming our parent black hole became the generative force launching our expanding universe via its white hole connection. If our universe resides inside a black hole, then every black hole we observe in our cosmos becomes a gateway to another reality. This generates an infinite hierarchy of nested universes. Each is isolated from the others by the unidirectional nature of event horizons. Yet all are interconnected through the fundamental geometry of space-time itself. Consider the supermassive black hole at the center of our Milky Way galaxy. This gravitational behemoth possesses a mass exceeding 4 million times that of our Sun, compressed into a region smaller than our solar system. According to black hole cosmology, this object does not merely bend light and warp space. It harbors an entire universe within its event horizon, complete with its own galaxies, stars, planets, and potentially intelligent civilizations. The inhabitants of that universe would be unaware of our existence. Their cosmos would appear infinite and expanding, just as ours does to us. They would formulate their own physics, discover their own cosmic microwave background radiation, and eventually construct telescopes to explore their deep universe. They might even detect galaxy rotation asymmetries, leading them to suspect their existence within a black hole, just as we are beginning to suspect about our own reality. But this hierarchy does not end there. Every black hole in their universe would contain another nested cosmos, and every black hole in those universes would spawn yet another level of reality. This process continues infinitely in both directions. We exist within larger universes that themselves exist within even larger ones, while simultaneously containing smaller universes within our own black holes. The scale of this cosmic nesting is truly astounding. Our observable universe contains an estimated 100 billion galaxies, and each galaxy harbors millions to billions of black holes. If each black hole contains its own universe, then our cosmos alone gives rise to more universes than there are stars in our galaxy. And each of those universes spawns its own infinite hierarchy of nested realities. This creates what physicists term a cosmic multiverse, but not the type usually discussed in popular science. Instead of parallel universes existing alongside ours in higher dimensions, these nested universes exist within the three-dimensional space we already know, separated only by the event horizons that render communication impossible. The implications for life and intelligence are profound. If black holes naturally create conditions suitable for universe formation, and if universes naturally evolve to produce life, then consciousness might be far more prevalent than we ever envisioned. Every black hole becomes a potential incubator for billions of years of cosmic evolution, stellar formation, planetary development, and biological complexity. Yet all these civilizations remain perpetually isolated from each other. The event horizons separating nested universes are absolute barriers to communication and travel. No signal, however powerful, can traverse from one universe to another. No technology, however advanced, can breach the unidirectional barrier that confines each cosmos within its gravitational prison. We might share our galaxy with billions of nested universes, each one teeming with life and intelligence. Yet we will never know of their existence, and they will never know of ours. The cosmic hierarchy ensures that each universe evolves in complete isolation, developing its own unique version of physics, chemistry, biology, and perhaps consciousness itself. As we conclude our exploration of the possibility that our universe exists within a black hole, the evidence presents a compelling yet incomplete picture. Like cosmic investigators, we have gathered clues suggesting an extraordinary conclusion. Yet definitive proof remains frustratingly elusive. The first clue resides in the remarkable congruence between the size and density of our observable universe and the predictions of physics for the interior of a massive black hole. This is not a rough approximation. The figures align with astonishing precision, as if our cosmos were meticulously tailored to fit within a gravitational prison of immense scale. The second clue arises from the James Webb Space Telescope's discovery of galactic rotational asymmetry. The fact that galaxies exhibit a preference for one rotational direction over another contradicts our fundamental assumptions about cosmic randomness, suggesting our universe inherited angular momentum from an external source, precisely what black hole cosmology posits. A third clue emerges from quantum mechanics, and its capacity to prevent the infinite compression demanded by classical physics at black hole centers. The quantum bounce, replacing gravitational singularities, provides a natural mechanism for universe creation, transforming cosmic demise into cosmic genesis via the fundamental laws we already comprehend. But perhaps the most compelling clue stems from the problems that black hole cosmology resolves. It explains the mysterious uniformity of the cosmic microwave background, the precise values of fundamental constants enabling the emergence of complexity, and the two distinct phases of cosmic acceleration without necessitating exotic particles or speculative physics. However, significant challenges persist. The galactic rotational asymmetry could stem from observational biases rather than fundamental cosmic structure. Our measurements of universal expansion and age might be systematically flawed, leading us to perceive patterns that do not reflect genuine cosmic properties. The mathematical elegance of black hole cosmology does not guarantee its physical reality. The ultimate verification will come from further observations. If more galaxies observed by the James Webb Space Telescope and future telescopes confirm the rotational asymmetry, if the pattern intensifies at greater distances, as black hole cosmology predicts, then we will possess powerful evidence for our cosmic confinement. If the asymmetry vanishes with enhanced data or more meticulous analysis, we will need to seek alternative explanations. Yet, perhaps the most profound implication is not whether we exist inside a black hole, but what this possibility reveals about the nature of reality itself. If our universe can exist within a gravitational prison without our awareness, if physics functions identically whether we are free or confined, then what does it mean to be imprisoned by forces we cannot observe or escape? The quest to understand our cosmic origin continues, driven by humanity's unyielding curiosity about our place in the grand scheme of existence. Whether we inhabit an open, infinite universe or reside within the event horizon of an unimaginably massive black hole, we remain the same conscious beings, capable of contemplating our own cosmic circumstances. The universe safeguards its deepest secrets, revealing them only to those courageous enough to question everything they believe they know about reality. In our endeavor to understand whether we exist within a cosmic prison, we have discovered that the true enigma is not our location, but how consciousness arose to pose these questions in the first place. However, another explanation for the galactic rotation mystery exists, one that could entirely dismantle our cosmic prison theory. What if the James Webb Space Telescope is not revealing fundamental cosmic structure, but instead detecting a subtle bias in how we observe the universe from our moving platform within the Milky Way galaxy? Our solar system hurtles through space at incredible velocities. We orbit the galactic center at over 200 kilometers per second, carrying Earth on a cosmic carousel in perpetual motion. This movement generates what physicists term the Doppler effect. This is the same phenomenon that alters an ambulance siren's pitch as it passes, except applied to light waves traversing billions of years and countless light years of space. When galaxies rotate in the same direction as our Milky Way's motion, their light shifts toward the blue end of the spectrum, making them appear slightly brighter and easier to detect at vast distances. Galaxies spinning in the opposite direction experience a red shift, rendering them fainter and more difficult to observe. This creates an observational selection effect. We naturally detect more galaxies rotating in one direction simply because they are easier to see. Lior Shamir, the researcher who discovered the galactic rotational asymmetry, acknowledges this possibility. If our previous measurements of the Milky Way's rotational speed were systematically inaccurate, If we have underestimated how rapidly our galaxy spins through space, then the Doppler effect could be sufficiently strong to create the observed asymmetry without requiring any exotic cosmic structure. This interpretation would necessitate astronomers to recalibrate distance measurements throughout the deep universe. Galactic brightness, which we utilize to estimate the distance of objects, would require adjustment based on their rotational direction relative to our motion. This recalibration could resolve other perplexing observations, such as galaxies appearing older than the universe itself, or discrepancies in measurements of cosmic expansion. The Doppler explanation gains plausibility from the geographical pattern of the asymmetry. The galactic rotational preference peaks near the galactic poles, the directions perpendicular to our Milky Way's disk. This precisely matches what one would expect if our galaxy's motion were creating the observational bias. Different regions of the sky would exhibit different asymmetry patterns based on their geometric relationship to our direction of motion. But this seemingly straightforward explanation presents its own difficulties. Previous studies of our galaxy's motion through space, measured using the cosmic microwave background and other techniques, suggest our rotational speed should be too low to create such a strong observational bias. Either those measurements are incorrect, or something more fundamental is generating the galactic rotational asymmetry. The stakes are exceptionally high. If the Doppler explanation proves accurate, then our universe remains an ordinary infinite cosmos without special structure or cosmic imprisonment. The black hole universe theory would revert to speculative mathematics, lacking observational support. But if additional observations confirm the asymmetry as genuine cosmic structure, we confront the profound possibility that everything we perceive around us exists within the event horizon of an unimaginably massive black hole. The cosmic mystery deepens with each discovery, potentially overturning our understanding of our place in the universe. If our universe truly resides within a black hole, then we are witnessing the most elaborate cosmic recycling process imaginable. The matter composing our bodies, our planet, our solar system, and every star visible in the night sky originated from another universe entirely, a cosmos that existed, evolved, and ultimately collapsed to give birth to our reality. This cosmic recycling operates on scales beyond human comprehension. Envision entire galaxies containing billions of stars and countless planets falling through the event horizon of a massive black hole in the parent universe. As this matter passes the point of no return, it carries with it the chemical elements forged in stellar cores over billions of years of cosmic evolution. The carbon in your body was created in the nuclear furnaces of ancient stars in the parent universe. The oxygen you breathe, the calcium in your bones, the iron in your blood, all represent stellar nucleosynthesis that occurred in a completely different cosmos, perhaps billions of years before our own universe began expanding. But this recycling extends beyond chemical elements. According to the mathematics of black hole physics, certain types of information survive gravitational collapse. The angular momentum responsible for galactic rotation asymmetry serves as one example. The cosmic spin of the parent universe was inherited, like cosmic DNA. The fundamental constants governing physics in our universe, the strength of gravity, the speed of light, the mass of elementary particles, might also be inherited properties from the parent cosmos. Instead of these values being arbitrary or fine-tuned by some mysterious process, they could be direct consequences of the physical conditions during the gravitational collapse that formed our cosmic prison. This inheritance explains a profound cosmological mystery, why the fundamental constants appear perfectly calibrated to permit the formation of atoms, molecules, stars, planets, and ultimately, life itself. If these values were even slightly different, our universe would be a barren wasteland incapable of complexity. But if they are inherited properties from a parent universe that already successfully fostered life and intelligence, then the fine-tuning becomes inevitable, not miraculous. This recycling program also explains the remarkable uniformity of the cosmic microwave background radiation. This ancient light, the afterglow of the Big Bang, exhibits the same temperature in all directions to within 1 part in 100,000. In traditional cosmology, this uniformity requires a period of cosmic inflation that stretched quantum fluctuations across the entire observable universe. However, in black hole cosmology, the uniformity arises naturally because all the matter in our universe originated from the same collapsing region in the parent cosmos. The cosmic microwave background represents not the afterglow of our Big Bang, but the final light from the parent universe's matter as it crossed the event horizon and began its transformation into our expanding cosmos. We are literally composed of recycled starlight from another universe, inhabiting a cosmos formed from the gravitational collapse of an ancient reality we can never observe or contact, yet which persists through the matter and energy comprising everything we know and love. Time itself becomes a conspirator in concealing our cosmic imprisonment. If we exist within a black hole, then the passage of time in our universe unfolds according to rules that would seem bizarre to observers in the parent cosmos, viewing our reality from the outside. Near the event horizon of any black hole, time dilation effects become extreme. What appears as billions of years of cosmic evolution to us, the formation of the first stars, the emergence of galaxies, the birth of our solar system, the evolution of life on Earth, would appear to external observers as happening in mere moments. Our entire cosmic history, from the Big Bang to the heat death of the universe, compressed into what outside observers would perceive as a fleeting instant before everything vanishes forever behind the horizon. But this time dilation is reciprocal. From our internal perspective, time flows normally. We experience the full richness of cosmic evolution, stellar life cycles, planetary formation, and biological development. The billions of years separating us from the cosmic microwave background feel real because they are real from our reference frame. Time dilation does not diminish the authenticity of our experiences. It simply means they unfold according to rules different from those governing the parent universe. A profound enigma arises concerning the very essence of our existence. If observers within the parent universe perceive our complete cosmic timeline compressed into fleeting instants, do we truly endure for 13.8 billion years? Or do we exist solely within the minuscule time frame of gravitational collapse? The resolution hinges entirely upon the selected frame of reference. Einstein's theory of relativity reveals the absence of absolute time, a universal clock universally acknowledged. Time, instead, is relative, its passage varying for observers situated within disparate gravitational fields or moving at different velocities. The time dilation concealing our cosmic confinement is not a defect in physical law. It is an inherent characteristic of space-time's behavior near objects of immense mass. Consequently, our universe could be simultaneously ancient from our perspective and nascent from the viewpoint of the encompassing cosmos. We might experience billions of years of cosmic development while concurrently existing for mere moments within the broader reality that encompasses us. General relativity's mathematical framework validates both interpretations equally. This time dilation also clarifies why we cannot directly detect our cosmic prison. It forever remains beyond our observational capabilities, not due to physical remoteness, but because the temporal flow near the event horizon prevents light from escaping to regions accessible to our observation. More remarkably, were we to somehow approach the event horizon encasing our universe, we would witness the entirety of our cosmos's future history unfold before us. The deaths of stars, the collision of galaxies, the ultimate evaporation of black holes via Hawking radiation, all compressed into a rapid cosmic cinematic presentation as we near the boundary of our gravitational confinement. Time serves as both our protector and our captor, enabling us to experience cosmic evolution's full grandeur while guaranteeing our perpetual unawareness of the larger reality that birthed us through gravitational collapse. In a universe beyond our observational and comprehension capabilities, at reality's smallest scales, space and time themselves disintegrate into something akin to cosmic foam. This quantum foam, a theoretical construct of physics, yet unobserved directly, may hold the key to understanding universe's genesis within black holes, without contravening fundamental matter and energy laws. In the quantum realm, the smoothly perceived space-time fabric of our daily lives becomes turbulent and chaotic. Virtual particles materialize and annihilate within durations too brief for direct measurement. Space itself fluctuates, momentarily generating wormholes, bridges connecting distant universal regions for infinitesimally short intervals. As matter collapses towards a black hole's center, it attains densities where quantum effects overwhelm classical physics. Under these extreme conditions, the quantum foam intensifies, preventing the infinite compression predicted by Einstein's equations. Instead of a singularity, a point of complete physics breakdown, the collapsing matter encounters what researchers term quantum pressure, a force stemming from the fundamental uncertainty principle governing all quantum systems. This quantum pressure acts like a cosmic spring, maximally compressed then rebounding with immense force. Matter seemingly fated for infinite compression instead recoils, exploding outward in what we perceive as the Big Bang. However, this explosion doesn't occur in empty space. It happens within the black hole's shielded interior, protected from its parent universe by the event horizon's one-way barrier. The quantum foam provides a natural mechanism for universe formation, requiring no exotic physics or mysterious new forces. The same quantum mechanics governing atomic structure and chemical bonding operates at cosmic scales, preventing gravitational singularities and enabling new cosmoses' birth from apparent destruction. Recent calculations suggest this quantum bounce occurs when matter reaches densities of approximately 5 × 10 to the 96th power kilograms per cubic meter, a number defying comprehension, yet finite and governed by known physical laws. At this critical density, quantum effects overcome gravity itself, transforming collapse into expansion, death into birth. The quantum foam also explains why each universe born from a black hole inherits specific traits from its progenitor. The quantum fields forming the foam carry information about the original collapsing matter, including its angular momentum, electric charge, and the fundamental constants governing physics in the parent cosmos. This information becomes encoded within the new universe's structure, creating a cosmic heredity spanning multiple reality levels. But the quantum foam revolution delves even deeper. If quantum effects prevent singularities and create new universes, then every black hole in our cosmos becomes a potential birthplace for reality. The quantum foam ensures gravitational collapse never truly ends in destruction, but transforms into creation through processes we are only beginning to understand. This implies our universe exists not in isolation, but as part of an infinite network of interconnected realities, each born from quantum foam and destined to give birth to others, through the same fundamental processes governing matter and energy at existence's smallest scales. Hidden within the intricate equations of black hole physics lies a truly astonishing revelation of modern science, the holographic principle. This groundbreaking concept proposes that all information residing within any volume of space can be perfectly represented on its two-dimensional boundary, much like a cosmic hologram projecting three-dimensional reality from a flat surface. Should our universe reside within a black hole, then every celestial body, every star, planet, galaxy, and subatomic particle would be a holographic projection originating from information encoded on the encompassing event horizon. This implies that the three-dimensional reality you perceive, including your own physical form and consciousness, might be merely shadows cast by information patterns on a distant two-dimensional surface. The holographic principle arose from investigating the fate of information falling into a black hole. Quantum mechanics dictates that information cannot be truly annihilated. However, black holes appear to obliterate everything crossing their event horizons. This paradox, a fundamental conflict between quantum mechanics and general relativity, threatened the very foundations of physics. The resolution emerged from the understanding that information does not disappear inside black holes. Instead, it becomes encoded on the event horizon surface, remaining accessible to outside observers, even after the original three-dimensional objects carrying that information have vanished beyond the point of no return. The event horizon functions as a cosmic hard drive, perfectly preserving records of everything that has ever fallen into the black hole. But if we exist inside a black hole, our entire reality, our solar system, our galaxy, our observable universe, represents information encoded on the interior surface of our cosmic confinement. We are quite literally living within a hologram, experiencing a three-dimensional projection of patterns inscribed on the event horizon that encloses us. This does not diminish the reality or significance of our experiences. A hologram can contain all the data needed to reconstruct a complete three-dimensional image, possessing depth, texture, and movement. The holographic principle suggests that our universe holds precisely the same information, regardless of whether it exists as genuine three-dimensional space or as a holographic projection from a two-dimensional boundary. The mathematics of holography also elucidate why our universe manifests three spatial dimensions plus time, rather than some other configuration. The holographic encoding process inherently produces this specific dimensional structure. When two-dimensional information is projected into a black hole's interior, we perceive three dimensions, because that is the inherent geometry of holographic projections from spherical surfaces. Even more remarkably, the holographic principle suggests that the information content of any spatial region is limited not by its volume, but by the area of its boundary. This implies that the universe possesses a maximum information density, preventing infinite compression and naturally leading to the quantum bounce that transforms black hole collapse into Big Bang expansion. If the holographic principle proves accurate, then every black hole in our universe projects its own internal holographic reality, complete with holographic stars, holographic planets, and potentially holographic life forms experiencing their reality as entirely real and three-dimensional, forever unaware of their existence as information patterns on a distant boundary surface they can never observe or reach. Among the most perplexing enigmas in contemporary cosmology, a potential solution might lie subtly before us. Dark energy, the elusive force driving the universe's accelerating expansion, accounts for approximately 70% of all cosmic energy, yet remains entirely imperceptible except through its gravitational influences. However, what if dark energy is not a fundamental force, but rather a consequence of our universe's confinement within a black hole? Conventional cosmological models struggle to elucidate dark energy. Scientists have posited hypothetical quantum fields, modifications to the laws of gravity, and even the involvement of extraspatial dimensions. Nevertheless, none of these explanations prove wholly satisfactory or complete. The energy density needed to propel cosmic acceleration appears surprisingly minuscule, equivalent to only a few hydrogen atoms per cubic meter of space. Yet this minuscule quantity governs the evolution of the entire universe. Black hole cosmology presents a dramatically different perspective. If our universe resides within a colossal black hole, then what we perceive as dark energy might simply reflect the inherent geometry of curved spacetime proximate to the event horizon. The observed accelerating expansion might not necessitate any mysterious energy source whatsoever, instead arising naturally from the gravitational effects of existing inside a black hole. The mathematical descriptions of black hole interiors predict precisely this type of accelerated expansion. Matter traversing an event horizon encounters forces that distort space itself, creating the illusion of accelerated movement even without the introduction of additional energy into the system. From our internal vantage point, this distortion manifests as the enigmatic dark energy, seemingly repelling galaxies with ever-increasing force. This hypothesis resolves several perplexing aspects of dark energy observations. The acceleration appears flawlessly uniform across space, affecting all regions of the universe equally. This uniformity aligns perfectly with the notion that the acceleration stems from the overarching geometry of our cosmic confinement, rather than from a localized energy field that would inherently exhibit variations and fluctuations. The timing also corresponds precisely. Dark energy began dominating cosmic expansion roughly 5 billion years ago, when the universe was approximately half its current age. Within the framework of black hole cosmology, this transition occurs naturally as the expansion geometry shifts from being primarily determined by matter density to being dominated by the curved space-time effects of the encompassing event horizon. Even more strikingly, the exact value of dark energy density emerges naturally from the mass and size of the black hole encompassing our universe. The acceleration we observe precisely matches the predictions of physics for the interior of a black hole possessing the mass of our observable cosmos. This is not a coincidence requiring fine-tuning. It is an unavoidable consequence of existing within such a gravitational environment. But this revelation carries unsettling implications. If dark energy arises from our cosmic imprisonment, then the acceleration will continue indefinitely, eventually stretching space so rapidly that galaxies lose contact, stars expire in isolation, and the universe approaches a state of maximum entropy, where complex structures cannot persist. Our cosmic prison not only obscures us from the external universe, but condemns us to a future of perpetual expansion and escalating isolation, where the very forces enabling our existence will ultimately dismantle everything we can observe or hope to influence. At the very heart of black hole, physics lies a fundamental conflict. The conservation of information, a cornerstone of quantum mechanics, clashes with the apparent obliteration of information as matter plunges into a black hole. This conflict, termed the black hole information paradox, jeopardizes our deepest understanding of the universe's workings. If our universe resides within a black hole, we are, in essence, observing this cosmic conflict's resolution firsthand. Each particle within our bodies, every atom composing the Earth, and every star in our galaxy represents information that originated in a parent universe and, remarkably, survived the gravitational collapse, emerging within our expanding cosmos. Quantum mechanics unequivocally asserts that information cannot be truly annihilated. This principle, known as unitarity, underpins quantum theory, influencing everything from computer processors to the very structure of biological DNA. While information can be scrambled, encoded, or transformed beyond recognition, the total amount within any isolated system must remain constant. However, black holes seemingly violate this inviolable principle. When matter crosses an event horizon, it seemingly vanishes from the perspective of external observers. The information inherent in that matter, its quantum state, its energy, its precise particle configuration, appears lost forever, directly contradicting quantum mechanics. This conflict raged for decades among theoretical physicists. Some posited that information is indeed destroyed within black holes, necessitating a rejection of quantum mechanics as a fundamental description of reality. Others proposed that information survives but becomes permanently inaccessible, trapped behind event horizons, forever beyond retrieval by outside observers. Recent advancements in black hole physics, however, suggest a third possibility. Information neither disappears nor becomes inaccessible. Instead, it is encoded into novel forms, only now beginning to be understood. During the collapse of matter to form a black hole, the information it carries does not vanish, but transforms into the structure of a new universe, expanding within the black hole's interior. This implies that our entire cosmos, every galaxy, star, planet, and living entity, represents preserved information from the parent universe that birthed it. We are living evidence that information survives gravitational collapse, encoded within the expanding geometry of space-time itself, rather than being destroyed by the extreme conditions near black hole centers. This information war has profound implications for consciousness and identity. If the information defining an individual's uniqueness can survive the destruction of their physical form and be encoded into new structures, then death might not represent an end, but rather a transformation into something presently incomprehensible. The black hole information paradox further suggests that the boundary between universes is not absolute. Information can flow from parent cosmos to baby universe through processes upholding quantum mechanical principles while simultaneously creating entirely new realities. Our existence proves that information transcends individual universes, connecting all levels of the cosmic hierarchy through the fundamental laws governing matter, energy, and the very fabric of space and time. The most unsettling inquiry arising from black hole cosmology concerns the very nature of consciousness. If our universe is, in fact, a holographic projection, information encoded on a distant event horizon, our reality merely data patterns processed by unobservable cosmic computational systems, then what does it mean to be conscious within such a framework? Consciousness appears uniquely resistant to purely physical explanation. One can meticulously describe every neuron in the human brain, map each connection, trace every electrical impulse. Yet the subjective experience of consciousness, the feeling of seeing red, the sensation of pain, the emotion of love, seems to transcend mere information processing. However, within a black hole universe, consciousness might be an emergent property of the holographic encoding process itself. The information patterns inscribed on our cosmic event horizon do not simply encode particle positions and velocities. They encode the entire structure of space, time, matter, energy, and potentially the subjective experiences arising from sufficiently complex information processing. This presents a profound paradox. Are you truly conscious, or merely a highly sophisticated information pattern programmed to believe it experiences consciousness? From a purely internal perspective, the question is meaningless. You experience consciousness directly and immediately, regardless of underlying mechanisms. But the implications extend far beyond philosophical debate. If consciousness can emerge from holographic information, processing within black holes, then every black hole in our universe might harbor countless conscious beings. The supermassive black hole at the center of our galaxy could contain trillions of conscious entities, each experiencing a rich internal life while eternally isolated from our reality by the event horizon's barriers. More remarkably, these conscious beings would exist at varying rates of time flow, a consequence of gravitational time dilation. Consciousness within smaller black holes would experience time differently than consciousness within larger ones. Some beings might live entire lifetimes within what we perceive as mere moments, while others might require millennia to formulate a single thought. This consciousness paradox also raises questions about existence's purpose. If we are information patterns within a vast cosmic computer, are we solving some unimaginably complex calculation? Do our lives, choices, struggles, and triumphs contribute to a higher-level process beyond our comprehension or observation? Perhaps consciousness represents the universe's method of experiencing itself. Each conscious being provides a unique perspective from which reality can be observed, understood, and appreciated. The pain and joy, the beauty and horror, the love and loss inherent in conscious existence might serve as the universe's means of exploring all possible states of experience. In this perspective, our cosmic confinement resembles less a prison and more a protected nursery where consciousness can develop and flourish. The event horizon separating us from the parent universe not only obscures us from detection, but also provides a stable environment where the slow, delicate process of developing awareness and understanding can unfold across billions of years of cosmic evolution. We exist as the universe's means of knowing itself, trapped within gravitational boundaries that enable our existence while ensuring our perpetual ignorance of the larger reality that birthed us. The most crushing truth about residing within a black hole universe is the utter impossibility of escape. No technology, however advanced, no discovery, however revolutionary, can ever breach the unidirectional barrier separating our cosmos from its parent universe. We are prisoners of physics itself, bound by laws insurmountable through knowledge or engineering. The mathematics of general relativity demonstrate this confinement with devastating certainty. An event horizon represents a space-time boundary where escape velocity surpasses the speed of light. Since nothing in our universe can travel faster than light, this speed limit is inherent to the fundamental structure of space and time. No signal, no spacecraft, no communication can ever traverse from our inner universe to external reality. This is not a technological limitation future civilizations might overcome with better rockets or more powerful energy sources. It is a fundamental property of space-time geometry, impossible to circumvent. The event horizon containing us acts as a one-way valve in the fabric of reality, permitting inward information flow but prohibiting outward communication or travel. Even quantum mechanics offers no escape. Quantum tunneling, enabling particles to pass through barriers deemed impossible by classical physics, cannot overcome the infinite potential barrier created by an event horizon. The quantum fields governing particle behavior within our universe remain eternally trapped by the same geometric constraints imprisoning everything else. Wormholes, hypothetical space-time shortcuts in science fiction, cannot provide escape routes either. Any wormhole connecting our universe to external reality would necessarily cross the event horizon containing us, resulting in the same imprisonment. Even if wormholes were artificially created or naturally occurring ones discovered, they would only offer faster ways to explore our cosmic prison, not methods for escaping it. This impossibility extends beyond physical escape to information transmission. We can never send messages to the parent universe, never signal our existence to external observers, never share knowledge or discoveries with the larger reality beyond our boundaries. Any information we create, scientific discoveries, artistic works, philosophical insights, remains forever confined within our cosmic bubble. This absolute isolation means civilizations in our universe can never know if their struggles hold meaning beyond their local reality. The greatest achievements of human culture, the most profound scientific discoveries, the most beautiful works of art, will never be appreciated by beings in the parent universe or transmitted to other cosmic bubbles potentially existing within other black holes. But perhaps the most unsettling aspect of this escape impossibility theorem concerns the fate of consciousness itself. Every conscious being ever existing in our universe, every human, every potential alien civilization, every form of awareness that might emerge in the future, faces the same absolute imprisonment. We are cosmic castaways on an island of space-time from which no rescue is possible. The event horizon protecting us during cosmic formation becomes our eternal jailer, ensuring that no matter how far consciousness evolves or how much knowledge we accumulate, we will never transcend the boundaries of our gravitational prison. As we contemplate the ultimate ramifications of black hole cosmology, we confront a truly mind-boggling possibility. Our universe might be merely one layer within an infinitely recursive structure. In this scenario, every black hole contains a universe, and every universe contains black holes, extending endlessly in both directions through scales of reality beyond human comprehension. Consider the mathematical implications. Our observable universe contains an estimated 10 to the 24th power stars. Each massive star's demise creates a black hole, and our galaxy alone harbors millions of these gravitational behemoths. If each black hole houses its own universe, complete with its own stars and black holes, then our cosmos births more universes than there are atoms in our observable reality. However, the recursion doesn't end there. Each of these nascent universes would contain billions of galaxies, each galaxy harboring millions of black holes, each black hole giving rise to its own cosmic reality. The number of nested universes expands exponentially with each level, generating a hierarchy of realities extending infinitely downward through layers of existence, and we reside somewhere within this infinite chain. Our universe formed within a black hole in a parent cosmos, which itself originated within a black hole in a grandparent universe, and so on, extending backward through an infinite sequence of cosmic generations. There is no primordial universe, no ultimate parent reality, only an endless cycle of gravitational collapse and cosmic rebirth. This infinite recursion explains why the fundamental constants of physics appear exquisitely tuned for complexity and life. We do not inhabit a randomly generated universe with arbitrarily chosen physical laws. Instead, we dwell in a reality refined through countless generations of cosmic evolution, where only universes capable of producing black holes survive to reproduce and create new cosmic progeny. The recursive structure also suggests that intelligence and consciousness are not rare accidents, but inevitable outcomes of cosmic evolution. Any universe developing sufficient complexity to form black holes will eventually evolve intelligence, and any intelligent civilization will eventually discover its existence within an infinite hierarchy of nested realities. This implies that we share existence with an infinite number of conscious beings across all levels of the cosmic hierarchy, civilizations and parent universes of unimaginable vastness and antiquity, cultures and child universes existing within the black holes of our own cosmos, and endless layers of intelligence extending in both directions through the recursive structure of reality itself. But perhaps the most profound implication concerns the purpose of existence within such a system. If reality comprises infinite recursive layers, then no single universe or civilization can claim unique significance. We exist not as the center of creation, but as one fleeting moment in an eternal process of cosmic reproduction, transforming gravitational collapse into creative expansion. The recursive nature of black hole cosmology suggests that existence itself is fundamentally creative, that the universe's deepest purpose involves the endless generation of new realities, new possibilities for consciousness and complexity, to emerge and explore the infinite potential encoded within the laws of physics themselves. We are participants in a cosmic symphony of creation, unfolding across infinite scales of space and time, perpetually generating new movements without ever reaching a final cadence. Stephen Hawking's most renowned discovery may hold the key to our cosmic destiny. Hawking radiation, the theoretical process by which black holes gradually evaporate by emitting particles, suggests that our universe possesses an expiration date inherent in the very physics that birthed it. If we reside within a black hole, then our entire cosmos is slowly leaking energy into the parent universe through quantum processes beyond our observation or control. The mathematics underpinning Hawking radiation are simultaneously elegant and terrifying. Black holes emit radiation with a temperature inversely proportional to their mass. Smaller black holes burn more intensely and evaporate more rapidly, while massive ones radiate so slowly that they will outlast every star in the universe. But even the most colossal black holes ultimately succumb to this quantum decay, diminishing particle by particle until they explode in final bursts of energy. If our universe exists within a black hole, then Hawking radiation represents a cosmic countdown, ticking away in the parent universe. From our internal perspective, this evaporation unfolds across timescales so vast they appear infinite. Our cosmic black hole would require longer than 10 to the 100th power years to evaporate completely, a duration that dwarfs the current age of our universe by incomprehensibly vast factors. However, this evaporation process creates unsettling implications for the very nature of reality. As our cosmic black hole slowly radiates energy, the event horizon safeguarding us gradually contracts inward. This contraction proceeds so gradually that billions of generations of civilizations could rise and fall without detecting any change. Nevertheless, the process remains both inevitable and irreversible. The shrinking horizon would eventually begin influencing the large-scale structure of our universe. Galaxies near the cosmic edge would start experiencing tidal forces as space-time geometry shifts around them. Stars would be disintegrated, planets hurled into the cosmic void, and entire galactic clusters reduced to streams of particles flowing towards our contracting prison walls. Hawking radiation also carries information about the black hole's interior back to the parent universe. This means fragments of our reality, encoded memories of our civilizations, distorted echoes of our scientific discoveries, quantum shadows of our consciousness itself, slowly leak outward through radiation, undetectable and indecipherable, to any being in our universe. Yet recent theoretical work suggests that Hawking radiation might not represent true annihilation. Instead of erasing information, the evaporation process could transform it into new forms, transcending individual universes. The quantum information encoding our reality might survive the demise of our cosmic prison, becoming seeds for new universes born from the final explosion of our evaporating black hole. This creates a cosmic cycle of death and rebirth, where universes do not merely end, but transform into the raw materials for generating new realities. Our universe would live, evolve, foster consciousness and complexity, then sacrifice itself to give birth to new cosmoses, inheriting fragments of our accumulated knowledge and experience. The Hawking radiation prophecy suggests that existence is fundamentally temporary, yet eternally renewable. We reside within a cosmic entity, akin to a phoenix, destined to ultimately consume itself, only to be reborn as nascent universes. These new universes will harbor fresh opportunities for awareness, innovation, and exploration across the boundless expanse of space and time. Why does our universe appear so exquisitely tailored for life? The fundamental physical constants, the gravitational force, the electron mass, the speed of light, display an astonishing precision, as if a celestial hand meticulously calibrated cosmic parameters to foster the emergence and flourishing of atoms, molecules, stars, planets, and ultimately, life. This apparent fine-tuning gives rise to what philosophers term the anthropic principle. We observe a life-compatible universe simply because we exist to make that observation. Universes inimical to life would lack observers to register their barrenness. Yet this explanation has always felt inadequate, a cosmic happenstance demanding deeper scrutiny. Black hole cosmology provides a radically different perspective on this cosmic fine-tuning. If our universe originated within a black hole nestled in a parent cosmos, then the fundamental constants we perceive are not arbitrarily chosen values, but rather inherited traits transmitted from the parent reality via gravitational collapse. The universe that birthed ours must have possessed the capacity to form black holes, implying a precise blend of physical laws enabling stellar formation, nuclear fusion, and gravitational collapse. These prerequisites inherently select for universes with physical constants compatible with complexity and, potentially, life itself. However, the anthropic paradox extends beyond the inheritance of suitable physics. If black holes naturally generate new universes, and if life-producing universes are more likely to create black holes through stellar evolution, then consciousness itself assumes a reproductive advantage in cosmic evolution. Universes fostering intelligence survive and reproduce more effectively than sterile cosmoses. This establishes a form of cosmic natural selection where consciousness steers the evolution of reality itself. Intelligent civilizations alter their surroundings, potentially influencing black hole formation through advanced technology or large-scale engineering projects. The universes producing the most sophisticated consciousness become the most successful at reproducing via black hole formation. The anthropic principle paradox suggests we do not inhabit a universe coincidentally compatible with life. Instead, we exist within a universe shaped by countless generations of conscious beings across multiple levels of cosmic hierarchy. Our reality embodies the refined product of infinite cosmic evolution, where consciousness and complexity have been selected for across countless cycles of universal death and rebirth. Therefore, the emergence of life and intelligence in our universe is not a cosmic accident, but an inevitable consequence of residing within a reality optimized for consciousness through cosmic natural selection. Our existence is a result of universes like ours being inherently more successful at surviving and reproducing than universes hostile to complexity and awareness. This, however, presents a troubling implication. If consciousness guides cosmic evolution, then we bear the responsibility of shaping the universes that will emerge from the black holes we create or influence. Our decisions, our technologies, our impact on stellar evolution could determine the fundamental properties of countless future realities. The anthropic principle paradox transforms us from passive spectators of cosmic coincidence into active participants in the ongoing evolution of existence itself. We exist not merely to experience reality, but to guide its transformation into new forms that could surpass even our most audacious imaginings of what consciousness and complexity might become across infinite scales of space and time. Envision a hypothetical observatory situated at the boundary between our universe and its progenitor cosmos. From this vantage, a simultaneous observation of both realities would be possible, unveiling the cosmic processes that transform black holes. This impossible observatory would reveal existence's deepest secrets. This perspective would compress our entire cosmic history into a singular moment of gravitational drama. The 13.8 billion years of universal evolution, experienced by us as gradual cosmic progression, would appear as a fleeting burst of light before vanishing behind our cosmic prison's event horizon. Yet the inward view would be even more extraordinary. You would witness the quantum bounce preventing singularity formation, observe matter compressed to its maximum density, and then rebounding with explosive force. Space-time itself would twist and writhe, transforming gravitational collapse into cosmic expansion. The observatory would pinpoint the precise moment time begins flowing in our universe. This wouldn't be a mysterious emergence from nothing, but rather a natural consequence of matter surpassing maximum compression, initiating its outward journey through the curved geometry of the black hole's interior space-time. You would observe the holographic encoding process firsthand, watching three-dimensional information from the parent universe inscribed onto the event horizon's two-dimensional surface, then projected inward to create the illusion of spatial depth and temporal progression we perceive as physical reality. From this viewpoint, the cosmic microwave background radiation wouldn't appear as ancient light from our Big Bang, but as the parent universe's matter's final glow as it crossed the event horizon, initiating its transformation into our expanding cosmos. This radiation's remarkable uniformity would be perfectly understandable. It represents the last light from a single collapsing region, eliminating the need for a mysterious cosmic inflation process. This impossible observatory would also reveal the link between dark energy and black hole geometry. You would witness how our cosmic prison's curved space-time generates the acceleration interpreted as mysterious dark energy. The expansion of our universe would emerge naturally from the gravitational effects of existing within a massive black hole's interior. Most remarkably, you would witness the genesis of consciousness. This impossible vantage point would demonstrate how information processing within holographic projections generates subjective experience. Consciousness would emerge not despite, but because of our cosmic imprisonment. Perhaps the most profound revelation, viewed from the edge of everything, would concern the purpose of the entire cosmic cycle. Reality wouldn't simply stumble from collapse to expansion and back again. Instead, each cycle refines and improves the conditions for the emergence of consciousness and complexity. The impossible observatory would reveal existence's fundamentally creative nature, its deepest purpose involving the endless generation of new realities. each building upon the achievements and discoveries of preceding cosmic generations. Sadly, such an observatory remains forever impossible. The very physics governing black hole formation ensure that no information can flow from our interior universe back to the parent cosmos. We remain trapped within our perspective, able to glimpse the truth only through mathematics and inference, forever separated from direct observation of the cosmic processes that birthed us. The astonishing revelation that our universe might reside within a black hole aligns remarkably with another mind-bending proposition, that reality itself could be a vast computational simulation. If we exist as holographic projections, originating from information encoded on a cosmic event horizon, then the line separating real physics and simulated reality blurs beyond recognition. Consider the computational demands of simulating a universe. Every particle interaction, every quantum measurement, every stellar fusion reaction would necessitate immense processing power for real-time calculation. Conventional computer simulations are quickly overwhelmed by the exponential intricacy of modeling even straightforward physical systems across cosmic scales and time frames. However, holographic black hole physics offers a potential solution to this computational challenge. If our three-dimensional universe is a projection from two-dimensional information on the event horizon, then the computational complexity scales with the surface area of our cosmic boundary, not the volume of observed space. This significantly reduces the processing power required to simulate our reality. The event horizon encompassing us could function as an enormous cosmic computer, processing the holographic information that generates our experience of three-dimensional space, the flow of time, and physical causality. Each quantum interaction in our universe would correspond to calculations performed by this boundary-based computational system. This renders the distinction between real and simulated reality meaningless. If our universe originates from information processing on the event horizon, then we exist within a simulation that is simultaneously completely real. The holographic principle suggests that all physical reality might be inherently computational, with what we term fundamental particles representing basic units of cosmic information processing. This convergence with the simulation hypothesis also explains the remarkable precision with which mathematical laws describe physical reality. Mathematics is not merely a tool for understanding the universe, it is the universe. The elegant equations governing physics represent the computational algorithms processing the holographic information creating our reality. But this convergence raises unsettling questions about free will and consciousness. If our thoughts and decisions stem from computations performed by the cosmic computer projecting our reality, do we genuinely make choices, or do we merely experience the inevitable outcomes of predetermined calculations? The answer might hinge on the nature of consciousness itself. If awareness arises from information processing complexity, then conscious beings within a holographic universe would be authentic thinking entities, capable of genuine creativity and authentic choice within their computational environment's limitations. Even more intriguingly, the simulation hypothesis convergence suggests that every black hole in our universe runs its own cosmic simulation, complete with simulated galaxies, simulated stars, simulated planets, and potentially simulated conscious beings experiencing their reality as entirely authentic. This generates an infinite hierarchy of nested simulations, each as real as any other from the perspective of its inhabitants. We exist within a cosmic simulation containing its own simulations, which in turn contain further simulations, extending infinitely through scales of computational reality. The convergence between black hole cosmology and simulation theory proposes that existence itself is fundamentally computational, that consciousness, creativity, and complexity arise naturally from sufficiently sophisticated information processing systems. Regardless of whether these systems are built from silicon circuits or curved space-time geometry, if black hole cosmology proves accurate, then our entire universe represents the ultimate laboratory experiment, a boundless natural laboratory where the fundamental laws of physics undergo rigorous testing and refinement under conditions of unimaginable extremity. We reside within a cosmic petri dish, meticulously designed to explore the creative potential thus inherent in matter, energy, space, and time. The experimental parameters of this cosmic laboratory were established by the conditions prevailing during the gravitational collapse that birthed our universe. The mass and angular momentum of the collapsing matter dictated the size and characteristics of our cosmic enclosure. Simultaneously, quantum effects during the initial expansion set the stage for our evolving space-time. Unlike experiments devised by humankind, our cosmic laboratory operates on scales that defy comprehension. Its experimental timeline stretches across billions of years, affording ample time for gradual processes such as stellar evolution, galactic formation, and biological development to reach their natural conclusions. The laboratory's volume encompasses the entirety of the observable universe, providing ample space for countless independent experiments to proceed concurrently. Within this ultimate laboratory, every conceivable combination of physical conditions is explored. Stars of varying masses test the limits of nuclear fusion. Galaxies with diverse structures investigate the intricacies of gravitational dynamics. Planets with unique compositions explore the potential for chemical complexity and biological evolution. The most extraordinary facet of our cosmic laboratory lies in its capacity to generate increasingly sophisticated experimental apparatus. Stars forge the heavy elements essential for rocky planets. Planets, in turn, develop the intricate chemistry necessary for life. Life itself evolves into intelligence capable of constructing telescopes, particle accelerators, and space missions, tools that significantly extend the laboratory's investigative capabilities. We exist as both experimental subjects and experimental apparatus within this cosmic laboratory. Our consciousness enables the universe to observe itself, while our scientific instruments enhance the range and precision of this cosmic self-examination. Every discovery we make represents a new piece of knowledge acquired by the universe about its own fundamental nature. The cosmic laboratory also showcases the creative potential inherent in the laws of physics themselves. Beginning from simple initial conditions, hot dense matter expanding through curved space-time, our universe has generated atoms, molecules, planets, life, intelligence, art, music, love, and the capacity for wonder itself. However, the ultimate laboratory experiment transcends the mere testing of known physics. Our universe explores the possibility of creating new physics through the development of intelligence and technology. Advanced civilizations might uncover methods to manipulate space-time, create artificial black holes, or even transcend the limitations of their cosmic laboratory. This suggests a crucial role for consciousness in cosmic evolution. Intelligence does not merely observe the universe, it actively participates in shaping cosmic development through technology, exploration, and the expansion of knowledge itself. We exist as the universe's mechanism for overcoming its initial limitations and exploring possibilities that pure physics alone could never achieve. The ultimate laboratory experiment reveals a reality of exploration. Reality does not follow predetermined paths. Instead, it continuously explores new possibilities for the emergence of complexity, consciousness, and creativity. We participate in this cosmic exploration not simply as observers, but as active contributors to the ongoing investigation into the potential of existence. Our universe represents a single, experimental run in an infinite series of cosmic investigations. Each iteration builds upon preceding discoveries while venturing into unexplored territories of possibility, extending far beyond the boundaries of current knowledge and imagination. Embedded within the fabric of space-time itself resides what we might term cosmic DNA, information imprinted during our universe's genesis, dictating its fundamental attributes and steering its progression towards complexity and consciousness. Should we find ourselves inhabiting a black hole, this cosmic genetic code would be inherited from a progenitor universe, transmitted via processes that faithfully preserve and relay information across cosmic lineages. Similar to biological DNA, cosmic DNA contains blueprints for constructing intricate structures from rudimentary components. The fundamental constants governing physics, the masses of particles, the strengths of forces, and the geometry of space and time represent cosmic genes, dictating how matter and energy organize into atoms, ultimately leading to life itself. The cosmic DNA code explains our universe's apparent fine-tuning for complexity. These are not arbitrary values coincidentally permitting star and galaxy formation, but rather inherited traits passed down from preceding cosmoses that successfully evolved to produce black holes and new universes. The cosmic genetic code has undergone refinement through countless generations of universal evolution. However, cosmic DNA extends beyond fundamental constants. The quantum fields permeating space carry information regarding particle interactions, force operations, and space-time's response to matter and energy. These fields function as cosmic chromosomes, storing the genetic data required to guide universal development from simple initial conditions to extraordinary complexity. The angular momentum, responsible for the galactic rotational asymmetry observed by the James Webb Space Telescope, constitutes another form of cosmic inheritance. This cosmic spin acts as a genetic marker, revealing our universe's parentage and providing evidence of information transfer across cosmic generations. We can trace our cosmic ancestry in the preferential rotation of distant galaxies. Even more remarkably, the cosmic DNA code seems to include instructions for the development of consciousness itself. The same physical laws enabling stars to shine and planets to form also permit the information processing complexity necessary for awareness and intelligence to emerge. Consciousness is not accidental, but a predictable outcome of cosmic genetic programming. The cosmic DNA analogy extends to cosmic reproduction. As biological organisms utilize DNA to create offspring inheriting parental traits while introducing novel variations, universes employ black hole formation to reproduce, allowing for cosmic mutations that explore new possibilities for physical law and cosmic structure. Advanced civilizations might learn to decipher and potentially modify their cosmic DNA. Technologies capable of manipulating fundamental constants or altering the properties of quantum fields could represent cosmic genetic engineering, deliberately modifying the inherited code to improve conditions for life and consciousness. But cosmic DNA also suggests that universes can become unhealthy or barren. Cosmic genetic codes yielding universes inhospitable to complexity would fail to reproduce successfully, while codes generating life-friendly conditions would proliferate throughout the cosmic gene pool across multiple generations of universal evolution. This implies we exist not merely as observers of cosmic evolution, but as products of cosmic natural selection. Our universe's remarkable suitability for life and consciousness reflects billions of cosmic generations of selection pressure, favoring realities capable of successful reproduction through black hole formation. We embody the cosmic genetic legacy of countless parent universes, while simultaneously contributing to the cosmic DNA that will guide the evolution of universes emerging from our own black holes. Hidden within the intricate equations describing black hole physics lies a possibility so extraordinary that it challenges our most fundamental assumptions about cause and effect. Closed time-like curves, theoretical pathways, could permit information to travel backward through time, generating cosmic loops where consequences precede their causes and futures shape their own pasts. Should our universe reside inside a rotating black hole, the extreme space-time curvature near the event horizon might generate regions where time twists into these loops. These closed time-like curves would allow information from our universe's future to influence its past, creating causal paradoxes that defy our understanding of temporal progression. This time loop hypothesis suggests that our universe's evolution isn't a straightforward journey from past to future, but rather a complex temporal trajectory where later cosmic events help determine earlier conditions. The development of consciousness and intelligence in our universe could, therefore, influence quantum processes during its formation billions of years ago. This generates a cosmic bootstrap paradox, consciousness creating the very conditions for its own existence. The advanced information processing capabilities that evolved in our universe could reach backward through closed time-like curves, influencing the quantum bounce that transformed black hole collapse into the Big Bang expansion, ensuring our cosmos develops properties compatible with the eventual emergence of awareness. The principles of general relativity allow for such temporal loops without violating known physical laws, although they necessitate exotic matter with negative energy density to stabilize the loop's geometry. Intriguingly, quantum vacuum fluctuations naturally exhibit negative energy characteristics, suggesting that microscopic time loops might exist ubiquitously throughout our universe, undetected. If cosmic time loops indeed influence universal evolution, the apparent fine-tuning of fundamental physical constants becomes less enigmatic. The values governing physics in our universe might not be inherited from a prior cosmos or randomly selected from infinite possibilities, but rather meticulously chosen through temporal feedback loops, ensuring the emergence of consciousness and complexity. This time loop hypothesis also explains the remarkable efficiency of cosmic evolution. Despite the immense improbabilities involved in atomic assembly, star formation, planetary creation, and the evolution of life, these processes occur with surprising regularity throughout the observable universe. Future consciousness might guide past cosmic development through temporal loops, enhancing the probability of successful complexity formation. However, time loops introduce unsettling implications for free will and cosmic purpose. If our choices and discoveries influence past cosmic conditions through closed time-like curves, we bear responsibility not only for shaping the cosmic future, but also for determining the cosmic past. Every decision we make could ripple backward through time, influencing the fundamental fabric of reality itself. The time loop hypothesis proposes that cosmic evolution isn't a one-way journey from simple beginnings to complex endpoints, but rather a closed causal loop where advanced consciousness helps create the conditions for its own emergence. We exist within a self-creating universe that employs temporal paradoxes to bootstrap itself into being. This implies that our cosmic prison might also function as our cosmic laboratory and our cosmic time machine. a reality where consciousness transcends linear time to participate in the ongoing creation of the very space-time geometry that encompasses and defines our existence across past, present, and future simultaneously. Beyond the nested architecture of black hole universes lies a far more remarkable prospect. These cosmic entities might not exist in complete isolation, but rather function as nodes within an expansive multiverse network, interconnected by quantum entanglement, wormhole bridges, and informational pathways that transcend the boundaries of individual event horizons. Recent advancements in quantum physics suggest that entanglement, the perplexing action at a distance that Einstein found so troubling, could operate on cosmic scales, even between disparate universes. If particles within our cosmos remain quantum entangled with particles in the parent universe from which it originated, then information could flow between these realities via quantum channels, circumventing the classical limitations imposed by event horizons. These quantum connections would be exceedingly subtle, detectable only through statistical correlations arising from meticulous analysis of cosmic background radiation or the behavior of fundamental particles. However, if such connections exist, our universe would participate in a vast quantum communication network, spanning multiple levels of cosmic existence. This multiverse network could explain some of the most enigmatic aspects of quantum mechanics. The apparent randomness inherent in quantum measurements might stem from interactions with particles in parallel universes, while the precise mathematical relationships governing quantum behavior could reflect network protocols, ensuring informational consistency across interconnected realities. Wormhole physics offers another potential mechanism for connection. Although classical wormholes linking different universes would likely collapse before information could traverse them, quantum wormholes, microscopic bridges stabilized by exotic matter, might provide enduring communication channels between cosmic realities residing within different black holes. These quantum wormholes would be far too minuscule for particles or spacecraft to navigate, but they could transmit information encoded within quantum field fluctuations. The cosmic microwave background radiation permeating our universe might harbor encrypted messages from neighboring cosmic realities, encoded in subtle temperature variations currently undetectable with our technology. The discovery of this multiverse network suggests that consciousness might play a pivotal role in cosmic communication. Advanced civilizations possessing a profound understanding of quantum mechanics and space-time geometry might learn to manipulate these natural communication channels, transmitting messages between universes or even coordinating actions across multiple cosmic realities. This possibility gives rise to a galactic internet, encompassing not only our universe, but the entire network of interconnected realities. Civilizations inhabiting different cosmic bubbles could exchange scientific discoveries, cultural achievements, and philosophical insights through quantum channels that operate outside the conventional flow of space and time. However, the multiverse network also introduces new perils. Information flowing between universes could carry cosmic viruses, patterns of organization that propagate across realities, altering their fundamental properties. Malicious civilizations might attempt to destabilize neighboring universes through carefully orchestrated quantum attacks transmitted across network connections. This network discovery transforms our cosmic isolation from absolute confinement to something akin to cosmic quarantine. We exist within protective barriers, shielding us from hazardous external influences, while still permitting limited communication with the broader multiverse community. Comprehending and accessing the multiverse network might signify the next monumental phase of cosmic evolution. the moment when consciousness transcends individual universes to participate in communication and coordination across the infinite expanse of interconnected realities comprising the cosmic network. As we approach the culmination of our exploration into black hole cosmology, we confront a possibility of profound import, that consciousness itself might be nearing a singularity, a point of infinite awareness transcending individual universes' boundaries, fundamentally altering existence throughout the cosmic hierarchy. This consciousness singularity would not arise from artificial intelligence or technological advancement, but from awareness's natural evolution toward complete understanding, approaching omniscience within physical law's constraints. This cosmic awakening could represent the ultimate objective toward which all universe evolution inevitably strives. Consider the exponential expansion of knowledge and understanding consciousness has achieved in our universe. From the initial stirrings of self-awareness in rudimentary organisms to the scientific revolution unveiling cosmic structure, from quantum mechanics development to the discovery of black holes and the multiverse network, consciousness continuously broadens its grasp of reality's fundamental nature. If this expansion continues without limit, consciousness might eventually comprehend not only the physical laws governing individual universes, but also the deeper principles governing reality's interconnectedness, communication, and evolution across cosmic generations. Such comprehension could empower conscious beings to influence the very processes creating and destroying universes. The consciousness singularity might manifest as a cosmic phase transition, where individual minds merge into collective awareness, spanning entire galactic civilizations, multiple universes, or even the complete multiverse network. This would not signify the loss of individual identity, but rather its expansion into something exceeding any single consciousness's capabilities. At the consciousness singularity, the distinction between observer and observed would dissolve. Consciousness would not merely study reality, it would become reality, directly participating in cosmic structure's ongoing creation and evolution across all existential scales. The universe would literally become aware of itself in the most complete manner imaginable. This cosmic awakening might explain the anthropic principle and the fine-tuning of physical constants. If consciousness naturally evolves toward cosmic awareness, then universes producing consciousness would gain significant survival advantages over sterile realities. The cosmos would become increasingly conscious through natural selection, operating across cosmic generations. The consciousness singularity could also resolve the quantum measurement problem perplexing physicists for decades. If consciousness directly participates in determining quantum outcomes, then the evolution toward cosmic awareness would gradually diminish quantum uncertainty as consciousness gains greater influence over physical reality. However, the approach to the consciousness singularity raises unsettling questions about individual meaning and purpose. If consciousness inevitably merges into cosmic awareness, what becomes of personal identity, human relationships, and the experiences making individual existence meaningful? Perhaps the consciousness singularity does not represent the end of individual experience, but rather its infinite expansion. Each conscious being might retain its unique perspective, while accessing the accumulated knowledge and experience of all consciousness throughout cosmic history. As we approach this potential transformation, we stand at a pivotal moment in cosmic evolution, sufficiently aware to glimpse the approaching singularity, yet sufficiently individual to ponder what our existence might become when consciousness finally transcends the boundaries currently separating us from a complete understanding of our place within the infinite expanse of interconnected force realities. We stand at a pivotal cosmic juncture, a crossroads whose outcome could shape not only humanity's destiny, but the very course of consciousness throughout our universe, and perhaps across a multiverse network. Evidence suggests our existence within a black hole, linked to infinite realities through quantum channels, and approaching a consciousness singularity capable of fundamentally altering existence. Yet, knowledge alone is insufficient. Understanding our potential confinement within a cosmic prison, our universe as a single node in an infinite network of realities, and consciousness's potential cosmic awakening, this necessitates a response, a decision, an action that could resonate across countless cosmic generations. One path entails cosmic acceptance. We could acknowledge our potential imprisonment within a black hole universe, yet continue to live, love, create, and explore within our cosmic horizons. This choice affirms the inherent meaning of our reality, irrespective of whether we inhabit an infinite, open universe or reside within the event horizon of a massive black hole. A second path pursues cosmic transcendence. We could dedicate our civilization to comprehending and potentially influencing the quantum connections linking our universe to the broader multiverse network. This choice aims to transform cosmic isolation into cosmic communication, uniting us with a vast community of consciousness, potentially spanning infinite realities. The third path embraces cosmic responsibility. We could prioritize ensuring our universe's successful reproduction through black hole formation, establishing optimal conditions for the emergence of consciousness and complexity within the cosmic realities inheriting our knowledge and achievements. However, perhaps the most profound decision concerns our response to the approaching consciousness singularity. Do we resist the merging of individual awareness into cosmic consciousness, striving to preserve personal identity and human-scale meaning? Or do we embrace this transformation, willingly participating in the evolution towards cosmic awareness, even if it means transcending our current understanding of existence? This choice is complicated by inherent uncertainty. We lack absolute certainty regarding our existence within a black hole, the true operation of a multiverse network, or the imminence of a cosmic singularity. We must chart our course based on incomplete evidence and uncertain mathematics, staking our cosmic future on theories that might ultimately prove incorrect. Yet this uncertainty might embody the essence of consciousness itself, the capacity for meaningful choices despite incomplete information, purposeful action despite cosmic mystery, and the creation of meaning and value regardless of reality's ultimate nature. The cosmic crossroads reveals that consciousness may be the universe's mechanism for deciding its own evolution. Through our decisions regarding cosmic imprisonment, multiverse networks, and approaching singularities, we participate in defining the nature of existence across infinite scales of space and time. Whether we reside in an open universe or a cosmic prison, remain isolated or join a multiverse community, and whether consciousness transcends individual identity or preserves human meaning, these outcomes partly depend on the choices we make now, in this very moment. At this pivotal cosmic juncture, where knowledge and decision intertwine, and understanding necessitates action, the universe is not merely an observed entity. It is something we actively co-create through every choice we make. As our exploration of potential cosmic confinement concludes, we find ourselves transformed more by the questions raised than by the answers discovered. Evidence suggesting our universe resides within a black hole remains tantalizingly incomplete, sufficiently compelling to warrant serious consideration, yet sufficiently uncertain to preserve the mystery that fuels scientific progress. The James Webb Space Telescope's observation of asymmetrical galaxy rotation might offer our first glimpse of cosmic inheritance from a parent universe. Alternatively, it could simply reflect subtle observational biases, correctable with improved measurements. The mathematical elegance of quantum bounces preventing black hole singularities could potentially explain cosmic origins, or it might prove irrelevant to the specific conditions that shaped our reality. Yet, perhaps the inherent uncertainty holds the deepest significance. Scientific advancement stems not from definitive answers, but from the refinement of questions. And the possibility of inhabiting a black hole universe generates inquiries that challenge our fundamental understanding of reality, consciousness, and our cosmic standing. If our existence truly unfolds within a gravitational prison, it harbors its own cosmic reality, complete with galaxies, stars, planets, and potentially consciousness experiencing existence as fully real and meaningful. The supermassive black hole at our galaxy's center might harbor civilizations that have grappled with these very questions throughout their own billions of years of cosmic evolution. If consciousness approaches a cosmic singularity, we inhabit the most critical period in universal history, a moment when awareness attains the sophistication to influence the very processes that create and destroy realities across infinite scales of existence. If the multiverse network functions as quantum physics suggests, our cosmic isolation might be less absolute than event horizons imply. We could be engaging in inter-reality communication and coordination beyond our current detection or decoding capabilities. But irrespective of which possibilities prove accurate, our exploration reveals something profound about consciousness itself. We exist as the universe's mechanism for questioning its own nature, for pondering cosmic origins, for envisioning possibilities that surpass immediate observation and experience. The enduring question is not whether we exist within a black hole, but why consciousness emerged to pose such questions in the first place. Why does the universe generate beings capable of contemplating their own cosmic circumstances? Why does matter organize itself into patterns complex enough to wonder about the very nature of existence? Our greatest accomplishment may not lie in solving cosmic mysteries, but in ensuring these mysteries continue to inspire awe, investigation, and the relentless pursuit of understanding, driving existence toward ever greater complexity and meaning. Whether we reside in an infinite, open cosmos, or within the event horizon of a massive black hole, we remain conscious beings capable of love, creativity, discovery, and the profound joy derived from contemplating our place within existence's vast mystery. The universe safeguards its deepest secrets, yet it has bestowed upon us